So why actually we need more statistics? Why not to use median and range always? So let me show you a situation where actually this way of describing data is not the best. So what you see here, it's our original sample where we have ordered values and we have representation of these values on the plot. You can see the plot looks a little bit strange. I mean, most of the values are located on the left side, but that's made on purpose. So this is statistics that we have, median values, min, max, and the range. That's exactly the same statistics as we computed before. Now imagine that in our sample we have an outlier or extreme value. So in this case, you can see in the last value, instead of 10.7, I have 15.7. Why I have it, it depends. It can be indeed an extreme value, a particular apple that has a very high sugar content, but it also can be measurement error. It can be a lot of other things. But let's say that we have this outlier. You can see that it's indeed the distance of the red point is from the blue point is very, very big. How it influences the statistics? Well, the good thing is that it will not influence the median. Median is very stable to outliers. However, of course, it will influence the max and consequently it will influence the range. So the range we got, it's almost more than 3 times larger than the range we have without outlier. So range, as well as mean and max, they're very sensitive to extreme values, to outliers. And therefore, we need to find a way to reduce this influence. Maybe we can compute range not for the whole values, but for the values without outliers. But in this case, we need to find out how to remove the outliers from the data, right? So how to detect the outliers. So let's talk about this. Well, the general idea is that we need to use quantiles. What is quantile? Quantile, it's a set of values that split the whole range of your values into equal portions. For example, median is already a quantile. It's a single value that splits all your sample into 50-50%, right? So you have 50% of the values, 5 values in this case, smaller than the median, and 5 values larger than the median. Of course, you can continue and split into more, for example, 3 equal portions, or 4 equal portions, or 10 equal portions, and so on and so forth. And every time, if you split your data into n equal portions, you need n minus 1 values, right? For example, in this case, we have 2 portions, but we need only 1 value to split the sample into 2 groups, right? For example, let's take 4 portions, 4 equal portions. In this case, we have 10 values. Of course, we cannot split 10 values into 4 equal portions as whole numbers, but let's take, let's say we have 2.5 value in each portion, right? So in this case, our quantiles will look like this. So you can see that between every quantile, we have 25% of the values, like 2.5, right? And these 3 quantiles that split our sample into 4 equal portions, we call them quartiles because it's 1/4, right? 25% is a quarter, so therefore we call them quartiles. So it's the first, second, and third quartile. 3 different quantiles which splits values into 4 equal portions. But how to compute quantiles? What's the general way to compute quantiles? In order to do that, let's start with our sample and let's try to define this percentage for every single point. How? Let's take the second value. So how many values we have smaller than this one? Well, apparently in our sample, we have only one value smaller than 9.4. So it's a 10%, right? So we can say that 10% of values is smaller than 9.4. So we can say that 9.4 is 10th percentile. Because percentile, it's exactly how many values are smaller than the given. So 9.4 in this case for our sample, it's a 10th percentile, right? Then we can continue and take the next value. How many values are smaller than 9.6? In this case, we have 2 values, which is because the total number of values is 10, it's a 20%, right? So it's a 20th percentile. And we continue until we calculate this percentage for all of them. And that's the kind of a percentile. So every value has a given percent. It's a percent of values smaller than this particular value. So this is the simplest way to compute sample quantiles. So when you define a percentage value for every value, it's called every value of your sample, it's called sample quantile. And usually sample quantiles, we represent them not in percentage, but just as a part of one, like this. And then you can see that we can find a mathematical expression that calculates sample quantile for any number of values for any particular value, right? So if you define the rank of values k, the value is x, and this percentage is p, then this is the expression, right? So you simply take a rank, subtract 1, and divide with the sample size. So this is the way to compute sample quantiles in this particular example. However, this way of computing quantiles has one drawback, especially for the small sample size. You can see that if you take the first value, we have nothing on the left, right? So we assume that 8.9 is already the smallest, 0% of values is smaller than 8.9. While here we have like a 10% gap, right? So, well, it's easy because 10.7, how many values below 10.7? It's 90% of the values. So it's not a problem here, right? But now, if you think about a population, if you take another sample, of course, there is still a chance to get a value smaller than 8.9 or larger than 10.7, right? So from that point of view, although this way of computing quantiles is good for our sample, it makes sense. From that point of view, it's not well generalized to the whole population, right? Also, if you think about median, where the median is here, right? So median is here because it has 50th% quantile. But we know that, in fact, median is between value 5 and 6, right? So this way of computing quantiles is a little bit counterintuitive. How we can fix it? Well, in fact, there are many different ways to compute quantiles. For example, if you use R to compute quantiles, you will find out there are 7 different ways to compute quantiles. And the way that I showed you is just the simplest one. We will use a specific way which makes the quantiles balanced, and it's also used in many other statistical tools. So therefore, I would like to introduce this one. But in general, of course, it depends on which software you use. It depends on the sample size. For big sample size, it actually doesn't matter which way to use. They will give you more or less the same quantiles. But let's stick to one particular. So this is it. First of all, the intuition. So the intuition is following. Let's think about not the values that we have, but the values that we have in between. For example, let's take a value between the first and the second value, right? So this one, it's like a median for these two, right? And if you consider this value, apparently 10% of the values in your sample below that and 90% above that, right? So we can say that here we have the 10th percentile because we still have 10% smaller than this one. Likewise, here we have the 20th percentile because we have 20% below this one, right? But now, how to define the sample quantile? How to define a quantile for value number 2? Well, value number 2 is located between the 10th and the 20th percentile. So apparently, if you use linear approximation, this value should have the 15th percentile. Likewise, the first value will have the 5th percentile, the third value will have 25th percentile, and so on and so forth. So if you continue, this is the percentages I computed. So 8.9, it's 5th percentile, and the last value, 10.7, it's 95th percentile. And now we can define a kind of expression that can compute these sample quantiles for any number of any sample size, right? So in this case, again, we have k as a rank of the value, and p is the percentage, and n is a sample size. So this is the way, right? So we just subtract a half of the rank and then divide it to n. And now you can see that they are perfectly balanced. So we have 5% on both tails, and also the median is located where we expect it to be located. And from that point of view, it's a little bit more intuitive for us, right? Because it's balanced. Okay, so we will stick to this one. Now you can see this is the 5th percentile. Again, you can say, but we don't have any value smaller than that in our sample. In our sample, yes, but in theory, of course, if it's a sample size of 10, apparently in the population, you may have values smaller than that. So that's perfectly fine to have it 5th percentile, as well as perfectly fine to have it 95th percentile. Moreover, I can show you that for the large sample size, it makes more sense. In this case, you can see a sample of size 100, and the dashed lines, it's the percentiles, the 5th percentiles that we computed. So in this case, you can see that if you compute the sample quantiles using the formula that I showed you before, you can see the 5th value will have a sample quantile of 4.5, while the 6th value will have a sample quantile of 5.5. So the 5th percentile will be in the middle, which makes perfect sense because now we have indeed 5% smaller than that. Likewise, here you can see that, for example, how I get 95th percentile. So it's a 95 minus 0.5, which is 94.5, right? And then divide to 100. That gives you 0.945, exactly what I have here in this table. And then the value number 96 with rank 96, right? So it will have a percentile 0.955. So the 95th percentile is exactly in the middle. And indeed, we have 5 values which are larger than the 95th percentile. So this formula, actually, this expression, this way of computing sample quantiles works well, especially for the large sample size. Okay. And then we have, you see, 5% of smallest values here and 5% of largest values here. This way of computing different percentiles, especially when we have this balanced way to compute percentiles, it provides us a very important tool to describe the samples and the populations. It's a tool where we compute most common values. So we always have extremes. And the idea is, if we want to compute a range of the values, let's take the extremes off. For example, let's take 5% of smallest values off, 5% of largest values off, and what is left, in this case, it's 90%. We will call it 90% of most common values, right? So 90% of values except these extreme tails. And that's the way to estimate the range. So we can estimate range not for all values, but only for the most common values. By using this way, we reduce the influence of outliers. We can call it interval of 90% of most common values. And these intervals we will use a lot in this course because it's used a lot in statistics, right? So 90% of most common values, or 95% or 80%, it doesn't really matter in this case. It's the values which are located in the middle. So the equal percent of values, smaller or larger, are simply rejected, right? So this is the way to reduce the influence of outliers. Now let's talk about how to compute percentiles if you have a limited number of values and you don't have a particular value that corresponds to this percentile. For example, if we get back to our sample of size 10, we know that we have 5th percentile, 15th percentile, 25th percentile, but what if we need 8th percentile? So in this case, we don't have a value that corresponds to the 8th percentile, but we can use a little trick, a linear approximation, and this is how it works. Well, first of all, let's find out 2 percentile values which lies on both sides of the one that we are looking for, right? So in this case, it will be the 5th and the 15th, because 8 lies between 5 and 15, right? Now, you have kind of 2 representation of your values. On one hand, you have these percentages. On the other hand, you have the real values, right? So in the percentages, you have the 5th and the 15th, and the 8th is located here, between the 5th and 15th, closer to the 5th percentile. So you can measure a total distance between these 2 values, and you can measure the distance between these 2 values, right? So you can see that the distance between the left boundary and the percentile we are looking for, the 8th percentile, is approximately 30% of the distance between these 2 boundaries, right? So this is the way to relate these 2 distances. But then we can do the same trick in the values, with the values, right? So we have these boundaries, 8.9, which is the 5th percentile, and 9.4, which is the 15th percentile. And then we have this value that we don't know yet, 8th percentile. And the idea is that the distance between this value and the left boundary and the total distance between the 2 boundaries should have the same ratio as the distances in the percentage space. So this can be written mathematically like this, right? So the ratio between the distances in X space should be the same as the ratio between the distances in the percentage space, right? So it means that the distance between X and 8.9 should be 30% of the total distance between 9.4 and 8.9. Okay. So now we can put all these distances that we already calculated. So in this case, we have 0.1 and 0.03, right? So this is 0.03 and 0.1. And then we have also this one, it's 0.5. So the ratio between these 2 distances should be the same as the ratio between these 2 distances. And that's the way to compute first of all, we compute the distance. It's 0.15 in this case. And then we know if it's 0.15, it's how far x is from 8.9. So we simply add 8.9 to this distance, and we get the quantile that we are looking for, 9.05. So this is the way to compute quantiles. If you have a small sample size, you need to use the approximation. Okay. And of course, you can generalize it. So if we remove particular values and replace them with some letters, for example, we, instead of this 8.9 and 9.4, we simply use x1 and x2. It's two boundaries, right? It's the boundaries of the interval. So we know that the value we are looking for is inside. And then instead of 0.05 and 0.15, we use also P1 and P2. It's the percentages of these boundaries. And now we can simply generalize this by using letters instead of particular values. And that leads us to this particular expression, which you can use to compute quantiles for any given P, right? For any percentage. Okay. And that's just an illustration how to use it. It's the same task. So we know that x1 is 8.9, x2 is 9.4, p1 is 0.05, p2 is 0.15. And what we are looking for, it's the value that corresponds to 8% percentage, right? So it's the 8th percentile. Now we simply put all these values into the expression that we derived recently, and that gives us exactly the same answer as we got before. It's 9.05. Okay. So this is how to compute quantiles, percentiles, and in the next video, we will talk about how to visualize them.